Hello, everyone. It's so great to see you all again virtually. A warm welcome to everyone. I am Anvindra Singh, Network Operations Engineer at SenRa. Today, we are going to continue our discussion on the all inspiring and exciting wireless communication technology that has disrupted the entire IoT universe into so many profound ways, and that is LoRaWAN. So, this particular webinar is the sequel of the LoRaWAN 101 that we had in the month of October. And the agenda for today's webinar is inspired by this quote that we can leverage the power of any technology at its maximum when we know its attributes in depth. So, over the past couple of years, we got this amazing opportunity every day to whether we are when providing network as a service to our projects, some POCs, or just proactive deployments, or when we are sometimes talking to our customers and trying to solve some network related queries, we have gotten some insights. And what we have learned from all that is that only when we are able to understand the ins and outs of the technology, we can leverage its potential at its maximum. So we thought of bringing everything together on the table for our customers, viewers, and public in general, so that everybody gets to have, on the same page, and we could discover solutions that push the human race forward. So that's the code that we were inspired by, and the agendas would be as follows. We will have a LoRaWAN 101 recap. So I would not assume everybody that is in the present webinar was there in the last webinar 101. So we'll have a short recap of that. Then we'll take a deeper dive into the LoRa modulation itself. We'll explore the ins and outs of it very technically. After that, we'll move forward to understand what are those determining factors that simply determine the RF performance of your wireless system in context to the IoT use cases. And finally, all this theoretical knowledge that we have gathered in the first three sections, we will have a small case study. That's the most interesting one. Let's see what we have for you. So I'll just list down the today's topics so that you know what you're going to be looking at, what's the glossary, what's the vocabulary that you're going to take home. We'll be first talking about the 101, as I said, a recap. And in between, when we will talking about the 101, we'll explore these terminologies, those technical jargons that you see in wireless communications. That is transmission power, path loss, RSSI, receiver sensitivity, and data rate. After that, we will take a leapfrog to LoRa modulation. And in modulation, we will start from the scratch. We'll first tell you what modulation at all means. Then we'll try and talk about the conventional modulation schemes that are there in the market. And then we'll talk about these two important factors, the code rate and the spreading factor. These are the two things that you will see every day when you're working on any solutions that you're going to bring with LoRaWAN. So this session on code rate and spreading factor is going to be very technical. After that, we'll be talking about the different RF factors that actually determine the RF performance of a system. We'll talk about the enclosure attenuation. We'll see how transmit height affects the range, how environment affects it, and how receiver height and so on. Things like that that affect the range performance of your system. After all these technical things that we'll understand in depth, we'll do a small case study of one of our projects that is actually running in one part of our country. So buckle up, guys. Let's begin this beautiful journey on LoRa. So I'll give you a recap of what we discussed last time. We started with a simple analogy to understand the path loss. So I asked all of you to just remember your best friend and think of as if he's standing on the roof of his house and he's trying to say something to you. And you are a d1 distance away from your friend. The amount of power that you are receiving is going to be essentially less, because when signals will travel in this path, there is a loss there's a loss that it has to incur in between. So the received power is essentially going to be lesser compared to what was at the source. The person who is standing a literally far distance away, that is d1 plus d2 distance away from the source, is going to also receive some power, but he isn't able to comprehend what's going on. And that is happening because our ears are sensitive to signals up to certain threshold. There is a sensitivity level of our ears, and below which we cannot comprehend the signal. So with this basic analogy that we had in the LoRaWAN 101, we came to understood these four things. That is, what is transmission power? It's the power irradiated from the source. Then we understood that the signals will incur some path loss when they are actually traveling a distance, and that is known as path loss, which is a function of distance primarily. And we understood that if we are talking about things in dB scale, then the received power is necessarily the transmission power minus the path loss. And then we understand that there is a threshold below which we cannot comprehend the signal, and that is actually decided by which communication technology that you're using, and that is known as the receiver sensitivity. With that basic understanding, with that simple analogy, we move forward to understand that why LoRa is a long-range communication technology. So comparing with Bluetooth or Wi-Fi, these technologies have a receiver sensitivity level in the order of minus 70, 80 dBm. Now, if you see LoRa, it has impressively low receiver sensitivity in the order of minus 140 dBm, and hence this technology is long range. We also understood from these 4 points that we have understood about PXP, received power, RSSI, and path loss. We also understood why, along with long range, LoRa is low power, because even if I would reduce my transmission power from 30 dBm to 10 dBm, I'm still getting the range that I want. But I needed something that is low power, because you cannot expect the IoT devices to be AC powered. We have to have them battery powered. So we needed technology that was both long range and low power. And that's where LoRa fits in real good. It's both long range and low power. Finally, we talked about something that is a trade-off of LoRa. So we purchased something that we wanted, that is long range and low power. But we gave away something that we actually didn't want, that is the data rate. We understood that data in wireless sensor network is in the order of some bytes, a few bytes, 10, 50, up to 100. So it's not that we are expecting our end devices to transmit a video which is in the order of gigabits or megabits. So we don't as necessarily need some data rate that is in the order of megabits or gigabits per second. We are good with some bits per second or kilobits per second. So we actually didn't want something like a very high data rate. So we traded off something that we didn't want, but got something that we actually wanted, that is long range and low power. So that's why the inventors of LoRa did a very clever trade-off, and as it is known for, that we bought something that we want, that is long range and low power, by giving something that we necessarily didn't want, that is a low data rate. So I will talk in little more brief on the low data rate, because that's going to form the bedrock of the next section, that is on the LoRa modulation. So in the past webinar, we discussed that there are different modes of operation starting from 5, 4, 3, 2, 1, 0. These are the different data rate options that are there, giving us different bits per second. So assuming that if our transmitter is actually using a data rate 5 signal to transmit a 10 bytes of payload, it's going to take 34 milliseconds. That is the calculation that we did in the previous webinar. What we understood from there that is, if we are using a data rate 5 signal, what that means is that you're going to have a receiver sensitivity of that signal standing at minus 124 dBm. The time on air that it takes to transmit 10 bytes of packet when using data rate 5 mode is going to be 34 milliseconds. But since your receiver sensitivity is going to die at minus 124 dBm, what that means is that you're going to travel some distance, but the point where your received power becomes near to minus 124 dBm, your signals are going to die off. However, if I simply decrease my data rate by going to the data rate 4 option, I'm actually increasing the time that it takes to transmit the 10 bytes of payload. That is 68 milliseconds. But what I'm getting, where I'm getting the gain here is that my receiver sensitivity for a data rate 4 signal essentially dropped down from minus 124 to minus 127. What that means is that the data rate 4 signal transmitting the same 10 bytes of packet is going to get a slightly longer range as compared to the data rate 5. So we understood this curve, that if I decrease my data rate, if I keep on decreasing my data rate, of course, I'm going to take more time to transmit the 10 bytes of payload that I have to, but I'm going to get a better receiver sensitivity and hence a longer range. So we then see this table by summarizing that lower the data rate, slower the transmission, yes, but longer the range. And then we discussed the table, and that actually made much more sense than it was actually doing previously. So the different modes of operation, that is data rate 5, 4, 3, 2, 1, 0. This is the bits per second that they offer us. Then the 10 bytes of payload, how much time it takes to transmit the 10 bytes of payload was actually tabulated here. And the receiver sensitivity of different modes of operation was actually tabulated. So we understood this, but we never questioned ourselves that why a high data rate gives you lesser time on air and not a very good receiver sensitivity and all of that stuff. So that is actually lying hidden somewhere within the modulation. And we wanted to cover this topic in depth, and we couldn't do it in the 101. So that's where we are going to start. So this section on the LoRa modulation is going to be super technically intensive. So let's start from the scratch. We'll first even talk about what modulation at all means. So at the end device, you're essentially capturing some information in the form of bits and bytes. All right. And these are known as the information symbols. When these information or symbols are captured by the end device, they have to be transmitted over the air to the gateway. But they cannot be just directly throwing away bits and bytes in the medium because medium doesn't understand that. So the medium, what the medium is good friend with is electromagnetic waves. So we have to first convert our information symbols into electromagnetic wave patterns. So that conversion, that transformation of information symbols into electromagnetic waves is known as the modulation. So if you're using an end device that is transmitting some information symbols, that the first thing that should hit your head is that it is actually converting those information symbols into electromagnetic waves that will be traveling to the medium. So assuming that if I'm trying to transmit 00, then I'll be actually using an electromagnetic waveform to transmit 00. Whenever we think of an electromagnetic waveform, the first thing that hits our mind is a sine wave. What's a sine wave? If we see the frequency versus time representation of sine wave, it's simply over the period of time doesn't change its frequency. It's just a constant frequency signal that is lying on the F1 frequency. That's a sine wave. So I'm going to use sine wave of fixed frequency F1 to transmit 00 payload. And at the receiver, I'll just do the reverse process. I'll do the demodulation process and say that whenever you will receive a frequency F1 of a sine wave, then you'll understand that the intended symbol that was transmitted from the transmitter was a 00. However, if I would want to transmit 01, would I want to use the same frequency F1 that I was transmitting in case of 00? No. What all I would do is that I will change the frequency. I will change the frequency of the sine wave to represent another symbol that is 01. And whenever the receiver would receive another F2 frequency signal sine wave, it will understand that 01 was the intended symbol that was transmitted from the transmitter. Likewise, for all the different symbols that I have, essentially 4 to the power 2 in case of 2 bits at a time, I'm having different frequencies to represent different information symbols. So what essentially I did was I uniquely mapped my information symbols into electromagnetic waves. And that was done using a modulation technique called a frequency shift keying. So modulation scheme is nothing but it is simply allotting unique electromagnetic wave patterns to your symbols, and how you're doing that is essentially decided by which modulation scheme that you are using. Now, the third thing that we understood was the spectrogram. So you see a frequency versus time representation of your signal, that is actually known as the spectrogram analysis of your signals. So we understood three things, right? We understood what modulation means. It's just conversion of symbols into electromagnetic waves. And that has to happen because electromagnetic waves are good friends with the medium. You cannot throw away symbols into the medium. You have to first convert them into electromagnetic waves. And that is done by modulation process. Now let's look at and apply this knowledge of modulation into understanding how it works in case of LoRa. So modulation in LoRa is proprietary. Note that it is a patented technology that was patented by Semtech in June 2014. The name of the modulation itself is LoRa. It is having a trademark on it because it was patented by the Semtech company. Now the modulation scheme that LoRa uses is a derivative of a chirp spread spectrum modulation technique. We saw frequency shifting modulation in the previous slide. The LoRa uses modulation scheme which is a derivative of chirp spread spectrum. What does that mean? What does big word mean at all? So if you want to understand, the oversimplification for this is rather than using a sine wave of fixed frequency, I'm going to use a chirp wave. And what a chirp wave is, it's a sine wave that changes its frequency of the period of time. If you analyze its frequency versus time domain, that is a spectrogram, the chirp wave essentially over the period of time changes its frequency. It starts from the lowest frequency and goes to the highest frequency. So it increases its frequency over the period of time. That all is chirp. Now, what I would want to do is to use this chirp and modulate my symbols. So I have 00, 01, 1011. I want to transmit that. Instead of using a sine wave, I'm this time using a chirp wave that looks like this. It changes its frequency from the lowest frequency to the highest frequency. Now for the modulation, that's the oversimplification of this process. I will break this chirp into two parts. That's going to necessarily give me two chopped chirps. The way that I'm arranging these two chopped chirps is actually going to define what symbol that I would want to transmit. Now note that on this line that I just highlighted, I could have chosen any of the frequencies to start with the first chop chirp, but I chose F3 frequency. I could have chosen F4, F2, F1. All of these frequency could have been the start frequency of my first chop chirps, but I chose F3 because that essentially defined what symbol I'm transmitting. I'll just cementify this concept by giving an example. Let's assume again that we have an end device and a gate. I would want to transmit 0, 0. If I would give you the amplitude versus time domain representation of a chirp symbol, that's going to be really difficult. So let's take help of a spectrogram. If you would want to transmit 0, 0, what all you would do is that you will just break down the chirp and get two chop chirps. The start frequency of your first chop chirp is going to be necessarily F1. And then the second chirp starts from the lowest frequency and tries to go to the highest frequency. And whenever this kind of a pattern of two chop chirps are received at the receiver, whenever the receiver will see that the first chop chirp starts from the F1 frequency, it will understand that the 0, 0 was the intended symbol that was transmitted from the transmitter. However, if I would want to transmit 0, 1 from the transmitter, what all I would do after chopping my chirp into two parts, the start frequency of the first chop chirp is not this time transmitting from F1, rather F2. So that's the subtle difference that you see in all the different chirp combination that you see. When you are using 1, 0, the start frequency, you just notice the start frequency. The start frequency this time does not start with F1 or F2. It starts uniquely from F3. So that's how modulation in LoRa works. You just chop the chirp into two parts. The two chop chirps that you get, the starting frequency of the first chop chirp is uniquely defining which symbol that you want to transmit. So the receiver, whenever it sees what is the starting frequency of the first chop chirp, it will understand which symbol out of the four that we actually want to transmit. So that's it. That's LoRa. Is it? No, we are just getting started, folks. So I said symbols. Whenever we think of an end device is actually capturing some sensor information. I'm assuming that all the different sensors that it has is essentially capturing information in just 8 bits package. So my bin fill level is ranging from 0 to 255. That could be mapped by just 8 bits. So I'm using 8 bits at a time to transmit to actually capture my sensor information. So if I'm having 10 sensors associated with my end device, then the total number of bits that I would want to transmit is 8 into 10. So I have 80 bits this time. Just think of it as if you have 80 bits that you would want to transmit. Are these bits going to go for the modulation? No. The first thing that it goes through is a whitening block. What whitening block does is that it removes the long strings of zeros and ones to aid clock synchronization. If you're a telco wizard, this statement would have meant like really easy to understand. What happens at a whitening stage is that your bit sequence is stored with a pseudo-random sequence. And that essentially removes the long strings of zeros and ones. And that essentially helps the receiver to do the clock synchronization. After this whitening, when your information sequence is stored with a pseudo-random sequence that is known to both transmitter and the receiver, the signals, the information bits will go to a FEC block. What FEC stands for is the forward error correction block. This is the thing that you really want to understand because that is something that you're going to encounter every day when you're working on LoRa. What forward error correction means is that you would actually be adding some parity bits to your information. Parity bits are added to your information to detect and correct errors. Now, note that you would want to add you would take 4 bits at a time and then add either 0, 1, 2, or 3 or 4 number of parity bits to your information sequence. So I repeat, if you're using a code rate of 0, that means you're not adding any parity per 4 bit of your information. But per 4 bit of your information, if you would want to add 4 parity bits, then you're using code rate of 4. That's all parity means. How many parity bits that you want to add per 4 bits of your information is defined by the code rate or CR that you're using for the transmission. After the forward error correction block, we go for an interleaver. What interleaver does is that it will shovel your bits around such that the bits are shuffled around the different symbols so that even if you're having a burst error, it's actually distributed in different symbols. So if you have been working on the wireless communication system, these 3 things would have made just a direct sense. But note that it's not the direct information sequence that goes for the modulation, but this whitened forward corrected interleaved block goes for the modulation. Even if all that I said didn't make a lot of sense to you, just remember that you're having 80 bits of information. These 80 bits of information goes through a grinder. which is having whitening, forward error correction, interleaving block. So the whitening and interleaving doesn't add anything, but forward error correction essentially adds some parity bits to your information, and you must be wary about it. All right. So what code rate means is that you're adding per 4 bits of information bits some parity bits. If you're using a code rate of 4, that means you're going to have a total bits of 160 that you want to transmit now. You started with 80 bits, but since you added 4 bits per 4 parity bits per information bits, you're actually now having total bits of 160. If you would have chosen any other code rate, that means 3210, you know how many total bits that you're going to get, because you're adding that many number of parity bits per board bit of information. Now you want to be wary about this because you started with 80 bits. If you don't know what code rate that transmitter is set to, you're actually going to see 160 bits of information transmitted over there, because that is something that goes to the modulation for chirp. You want to know that if you're having a higher code rate, you higher the code rate, that means you're adding redundancy to your system. You're adding redundancy to a different information symbol. What that does is that it makes the signal immune to interference. But at the same time, since you started with 80, you went to 160 using CR4, you're essentially taking more time on air to transmit the pipes. However, if you're using a lower CR, the lower the code rate is, you're more prone to interference. You cannot detect and correct errors because you're not adding any parity bits. But at the same time, you are not going to take more time on air to transmit because you started with 80, but you didn't go to 160, but just 80 or 100 and 120. So that's a difference. That's a subtle difference. And this particular thing that I'm just saying right now is the sole reason that we put together this slide, because it is important to note that when you are transmitting the LoRa signal, which code rate that you have set your transmitter to, because that is going to make or break your RF performance. Cool. So that is about code rate. The next thing is about spreading factor. I'll just revise all the things that we've discussed so far, and then we'll try to understand what spreading factor means. We understood that LoRa uses a chirp spread spectrum modulation technique. Note that it's a derivative of CSS. It's not exactly the CSS. Now, chirp is a signal that we understood changes its frequency from a lowest frequency to a highest frequency. So when we compare a chirp with a sine wave is having a constant frequency over the period of time. Chirp, however, changes frequency from the lowest frequency to the highest frequency. So we are just going to use this chirp to modulate our symbols. That's it. Now you need to understand that what symbols mean. So symbols is essentially taking some bits at a time and doing the modulation, right? So if you're taking n bits at a time, you're essentially be having 2 to the power n different combination of your symbols. N is essentially known as spreading factor. The number of bits that you're taking at a time to create your symbol is actually the definition of spreading factor. So that is something that you see a lot when you're working on LoRa. The number of bits per symbol is essentially the spreading factor. So we saw what chirp means. Chirp is starting frequency from the lowest frequency and going to the highest frequency. All right, that is the kind of a waveform that chirp gives in a spectrogram analysis. The chirp essentially comprises of many different small chips. Right, the number of chips that a chirp has is defined by the spreading factor that you're using. So higher the spreading factor, higher the number of chips that are being accommodated within a single chirp. So the chirp is going to have 2 to the power spreading factor number of chips in your symbol. The chip time, the amount of time for which your chip is going to dwell at a certain frequency, is defined by solely bandwidth. So the chip time, the amount of time for which that tiny frequency component is going to dwell on the air, is defined by the bandwidth. So chip time is essentially defined by the inverse of the bandwidth. What that means is that your chip is going to take, or your symbol is going to take chips into chip time amount of time to transmit. That is 2 to the power spreading factor into 1 by bandwidth. So that's the total time that your symbol is going to take when you're using a spreading factor SF. Higher the spreading factor, now you can see that higher the spreading factor, more is the symbol time that you're going to take to transmit one symbol. Lower is the spreading factor, you can directly see that the symbol time is going to be less. What all we would do from this is that we will just change the start frequency of the two chop chirps, and the start frequency of the first chop chirp is going to define what exactly the symbol that you want to transmit over there. So the start frequency of the chop chirp, the first chop chirp, represents the symbol that you want to transmit. Now we are going to take SF bits at a time from the interleaved matrix that we see. We understood that that it's not the direct information sequence that goes into the modulator circuitry. No, it first goes through a variety of different blocks, that is forwarded correction, whitening, and interleaving. And then we would take some bits at a time from this interleaved matrix and do the modulation. So let's see what it looks like. So if I'm using spreading factor 7, this is the interleaver matrix that I have. I will take some bits at a time. But since I'm using spreading factor 7, that means that I'm going to take 7 bits at a time, and that will create my one symbol. Note that if I want to transmit another symbol, that means I'm going to take 7 bits at a time from this 160-bit matrix and then comprise my one symbol. In the other case, on the other hand, if I'm not using SF7 but rather SF8, what that means is that I'm not going to take 7 but this time 8 number of bits from this interleaving matrix and then comprise my symbol. So that's how you could see a subtle difference between the number of bits that you have in case of spreading factor 7 symbols and spreading factor 8 symbols. We necessarily have 160 bytes. We could use spreading factor 7 or spreading factor 8. With our understanding, now we know that the total number of symbols that are going to be comprising when you're using spreading factor 7 is going to be 23. That's just basic unitary method. I'm just dividing 160 by 7 and 160 by 8. So the total number of symbols that are going to be made out of this interleaver matrix is actually different in both the spreading factor 7 and spreading factor 8. I'm taking 7 bits at a time. The total number of symbols are going to be 23. I'm taking 8 bits at a time. That means total number of symbols that I'm going to form out of 160 bits is going to be 20. Now, from our knowledge, now we know that when I'm using a spreading factor 7, the number of chips that my chirp are going to accommodate is going to be 2 to the power spreading factor. In case of spreading factor 7, it's going to be 128. It's in case of spreading factor 8, it's going to be 256. The chip time, since we now know that for a fixed bandwidth that I have considered 125 kilohertz, is fixed for both spreading factor 7 and 8 because it's solely the function of bandwidth. It's 8 microseconds for both of these. Now, the symbol time is necessary, as we understood, is the chips into chip time. Now you see the subtle difference. That's where I wanted to mathematically define that the symbol time for the spreading factor 7 and spreading factor 8 is drastically different. And that has happened because the number of chips that we had, that is subtle difference for 7 and 8. So you see that symbol time is actually getting twice in case of spreading factor and spreading factor 8 more than that. So that is the subtle difference that you want to observe. And now you will calculate the total time, the total symbols that you have in case of spreading factor 7, that is the multiplication between the symbols and the symbol time. The total time that your symbols, the total time that your packet is going to take in order to transmit using spreading factor 7 is drastically different in case of spreading factor 7 and spreading factor 8. You see, you're taking 80 bits, you had whitening, you had forward correction, you have interleaving. Since I have assumed that I have used score rate of 4, 160 bits of information had different behavior, and hence the total packet time that it takes to transmit that packet is different for spreading factor 7 and spreading factor 8, and that's how the difference comes in. Now that was too mathematical. I will just give you a basic analysis for all those that are not telco wizards. Just assume that when you're using a spreading factor 7, the upcurve looks like this. It starts from the lowest frequency and goes to the highest frequency. Of course, it comprises of chips, and chip is defined by the number of spreading factor that you're taking, right? With the 2 to the power 7, that is going to be 128 chips. So you're having 128 chips accommodated between one chirp. Now, if you want to map basically a symbol, you will just chop this chirp into 2 parts. The start frequency of the first chirp is going to define what symbol that you want to transmit. So that's how it's going to look like when you would want to transmit 0110100 symbol, for example. For another symbol that is different bit combination of this 8-bit sequence, the start frequency of the first chirp is essentially going to be different. So that's how you're going to differ the two different symbols in case of spreading factor 7. Now note the subtle difference. Note the visual difference between spreading factor 7 and spreading factor 8 in the frequency versus time domain. In case of spreading factor 7, you know that there are 128 chips. In case of spreading factor 8, you now know that there are 256 chips that have to be accommodated in between. So that's steep. The slope has essentially gotten lesser. You see the curve, the ramp, the way that we are moving from frequency L to frequency H is essentially lessen in case of the spreading factor 8 symbol. So your ramp, your spreading is basically gotten lazy when you were increasing the spreading factor, and that's a subtle difference. That's a visual subtle difference that you could see when you're using spreading factor 7 symbol and you're seeing spreading factor 8 symbol. So now you'd be chopping this chirp rather than the SF7 chirp into two parts, and then you're going to map your symbol. And the start frequency of those different symbols is basically redefining the symbols that you would want to transmit. So that's the difference that I wanted to point out. If you're using a spreading factor 7, your chirp, your up chirp is going to be different from what it's going to be in case of spreading factor 8. It's going to take a lot of time to transmit the up chirp or the symbols, and that's how you could visualize it on a frequency versus time domain using the help of a spectrogram. So we understood things mathematically, we understood things visually. That's now the time that we see a spectrogram of an actual LoRa signal. Enough of a theory. We'll see an actual signal that we have captured at our labs, and this is the frequency versus time representation of that signal. It had some up chirps, and then there was some chop chirps that you see. Now you see that at least you have this small understanding that these chop chirps are representing the different symbols that I wanted to transmit. So the preamble sequence is comprising of some up chirps that helps the end device or the gateway, essentially the receiver, to understand that, hey, heads up, the data is about to come. Then there's a starting of the frame delimiter to tell the receiver that, hey, preamble is over, now you will be seeing some packets. And these chop chirps are actually your packets. So that's how you could basically disintegrate a spectrogram of a LoRa signal. Now, in case things that we discussed were a bit complicated for someone who's actually seeing these things for the first time, just remember that that frequency was just time representation of a spreading factor 12 signal would look like this. It will have some up chirps, then some spreading factors, starting of the frame delimiter, and then you're having some symbols on chirp. In case of a spreading factor 11 symbols, when you're decreasing the spreading factor, what all you're doing is that you're basically taking less time to transmit your symbol because your slope is essentially gotten higher. Your slope essentially increases when you're decreasing the spreading factor, the slope of the chirp I'm talking about. So that's why when you see different spreading factor symbols, you see that higher the spreading, lower the data rate because I'm taking more time per symbol and hence the total time increases. But since I'm taking long time per symbol, it gets easier for the receiver to comprehend that signal. So if you want to understand that mathematically, then we'll have to go into the depths of the CSS because higher the spreading factor, then there is a processing gain that gives you a low bit error rate and a small SNR, but that discussion is separate. Note that when you're using a higher spreading factor, you're taking more time to transmit per symbol, and that makes the receiver to understand that symbol easily. So that's why higher the spreading, lower the data rate, yes, slower the transmission, but longer the range because the receiver has an easy time to comprehend each of the symbol one by one. So that's the key idea. That's the visual differentiation between spreading factor 12, spreading factor 11, and so on. So we are now almost done with the heavy technical discussion that I wanted to bring in. I'll just summarize things for you. That within the technology, we saw that there are different modes of operation that allow different RF performance. We understood this table that there are different data rate modes that are available that are actually defined by the spreading factor that you're using. Higher the spreading factor, more the chips that you have to accommodate within the chip, and that essentially increases the time on air that you would want to transmit your 10 bytes of packet. But lower the data rate, you're basically seeing a impressively low receiver sensitivity because the receiver has an easy time to comprehend each of the symbols separately. So, but the key point that you would want to note here is that within the technology, there are different modes of operation that allow different RF performance. That's the point that you would want to clearly note. Because if you're using a spreading factor 8 symbol, it's going to get a range really higher than the short range communication technology or medium range communication technology. But compared to SF9 signal, it's not going to get that range because its receiver sensitivity level is different. All the different spreading factors have their own receiver sensitivity level. That simply means that they're going to cover different RF performances. All that implies to us that there are factors involved that affect the RF performance of the system. And the three factors that we have already now very comfortable with is the spreading factor, transmit power, and code rate. We now know that higher the spreading factor, longer the range. Code rate helps you get immune to interference. Transmit power is really intuitive. Higher the transmit power, more the path loss that you could incur, and hence higher the receive power you could get. Are there any other factors involved that we must be really educated about that actually impacts our RF performance? Yes, and that's exactly the section 3. We are now going to be talking about, this section is going to be very intuitive, the different RF factors that are involved that change the RF performance of a wireless system in context to the IoT use cases. So the first big factor that we wanted to bring in was the enclosure. All right. So different use cases, if you would see in a smart city, it could be a manhole monitoring sensor, it could be a street light controller, it could be a water meter, gas meter, all different use cases. They all demand different enclosure types, right? All these different enclosures have their own physical properties. What that means is that when signals will penetrate, when they start their journey to the gateway, they'll first have to penetrate through that enclosure. When they will penetrate through that enclosure, they're going to incur some attenuation. That will decrease the received power that is going to get out of the enclosure. So the signals that are going, that are penetrating to the enclosure are going to incur some attenuation, due to which the received power is going to be different when they come out of the enclosure. Now that attenuation, this problem is thoroughly researched and worked out in wireless communication system. And you see a table like this. For a glass attenuation, I mean the enclosure, if it is a glass of 6 millimeter thickness, it's going to offer you 0.8 dB of attenuation. So when you start with some transmit power, 0.8 dB is already lost when you're using a glass of 6 millimeter as an enclosure. If I'm using a glass which is having a 13 millimeter of thickness, it's going to have a higher attenuation. That is not very different from the 6 millimeter one, though. But the one thing that you must really notice is that when you're having an enclosure of concrete of a thick length, as you will see in case of water meter or in case of a manhole monitoring sensor, the attenuation is really huge. It's 35 dB compared to 2 or 0.8 dB that we are seeing. What all that means is that if you're using a use case, which is manhole or a street light controller with the same transmission power, I'm using the same transmit power to transmit my signals, same modem, all of things are the same. But since the enclosures are different, the enclosure attenuation are essentially different, and hence when the signals would come out from that attenuator, they're going to have different signal streams. So that's the thing that you would want to know. What is the enclosure that your solution is going to offer you? And you would want to work out that on that particular enclosure attenuation. That is one thing. Second, the most important of all is the transmission height. So let's assume that we have a manhole monitoring sensor and you are having a gateway that is residing on top of 3-4 story building, or not a very tall. The pole is like 2 meters of height. Whenever your manhole monitoring sensor, after it has incurred the attenuation due to enclosure, will see directly the gateway. I hope that is what I hope that is something that always happens, but it's not the case, because you're making solutions where line of sight path is essentially not possible, because you see a variety of different obstacles in between. So what happens is that whenever your signals would try to transmit, they would first have to diffract from the obstacle and then receive the gateway. Of course, that is going to give you a diffraction loss compared to what it was not there when there is a line of sight path condition. One thing that I would want to point out here is that there's a multipath propagation that is known in wireless communication. The signals would not just diffract, but they will refract, defract, they will simply refract from different obstacles and then reach the gateway. And the gateway will be going to superimpose all those different attenuated and time delayed version of the ensembles of the signals and then do the superimposition. But that is not the topic that I want to consider. But note that the diffracted signal is mostly considered to be having the highest signal strength. So assuming that I'm having a manhole monitoring sensor, which is going to incur some diffraction load reaching to the gateway, the same point in Earth, if I have a street light controller, then it's going to incur some attenuation and then reach the gateway. This diffraction loss is going to be necessarily different when we are comparing it with the manhole monitoring sensor and the street light controller. So how does that how that diffraction loss is differing when the height of the transmitter is different could be understood with the theory of diffraction. So we'll go to the high school math and see what theory of diffraction has to teach us. For a fixed distance from the obstacle and height h1 and h2 from the ground, like this, like you have a transmitter on the left and you have a receiver on the right, both of them are h1 and h2 distance away from the ground. Now, when the signal will transmit from the left side, that is the transmitter, they will diffract and then reach the gateway. There will be an attenuation associated with diffraction, and that is going to be, let's say, 60 dB. However, that diffraction attenuation essentially decreases with increase in either of H1 and H2. So if I would increase the height of H1, what all is going to do is that it will decrease the attenuation that your information that your electromagnetic signals are going to offer when they are going to get diffracted. So that's the subtle point that you would want to know, that any of the height H1 and H2, if they are high, that means that the diffraction loss is going to get lesser. So if you are having a signal that is going through a diffractor, what all is going to happen is that there is going to be a diffraction attenuation, and a signal is going to have a lesser signal strength passing through it. So if you're using a use case, again, taking an example of manhole and street light controller, both of them offer different transmitter height, right? You see a height of 0 meters in case of manhole monitoring sensor because you're starting from the base of the road. However, you have an upfront height gain of 10 meters when using a street light controller. We saw that the enclosure attenuation is, of course, is going to be different. But the point is that due to the change in the height, the point to note here is that the change in the height of the transmitter actually affected the diffracted attenuation of the strongest signal path that we have considered. And assuming that the path loss attenuation is same for both of these, the signal strength that you see at the receiver is drastically different for both solutions that started their journey from same point on Earth. That is the difference that you would want to know, that within the same time space, when you started your journey, different use cases gave you different signal strengths. Now we saw the different negative aspects of wireless communication. Is there a silver lining at all? Yes. And that's where deployment comes in, and that's where network operators will help you. When you're having obstruction in between, you're starting your journey from the manhole monitoring sensor, you saw that your gateway is having a height of, say, 4-story buildings along with a 2 meters of pole. Your signals have to diffract to reach the gateway. However, if your network operators are smart, they're going to deploy the gateway on a tower of impressively large height. What this will do is that it's going to offer a direct line of sight condition to your manhole monitoring sensor, which is starting from the base. And that part is really going to change the entire journey of your system, because this time, since you're directly seeing the gateway, there's a direct line of sight condition. You're not going to incur the diffraction loss, the direct line of sight condition. So that's how a deployment, the deployment of the gateway is actually going to make or break the RF performance of your system. If you're having a high tower, that means that you're going to get a larger probability of direct line of sight condition. Speaking of deployment, let's talk about what are the key characteristics of a professional deployment. If you want to see that deployment is professional or not, then these are the things that you would want to see. A massive receiver height. We saw from the previous example that if we increase the height of our gateway, it increases the probability that your signals are going to see the direct line of sight path condition. And that would change the signal strength of your signals at the receiver from bad to excellent. Even if the height is not that great and the obstacle height is really large, even if you're present somewhere here, your signals are going to incur some less diffraction, because we understood now from the theory of diffraction that if any of the heights are increased, your signal is going to have lesser diffraction loss, and that necessarily means a good signal strength at the receiver. We understood that it's up to the use case. If you're having a manhole monitoring sensor, then you have to have an enclosure. You have to have it dig inside 1 feet below the ground. That is something that you cannot change. It's only specific to the use case that you're working on. So you're fixed with the transmitter height depending upon the use case that you're working on. But the variable is the gateway height, and that is up to the network operators. They have to tie up with the good tower companies and deploy their gateways on a really impressive height. And that is going to do two major things that we have understood technically: that increases the probability of the direct line of sight path condition, and also if not direct line of sight path condition, it is actually going to reduce the diffraction loss, because either of the H1 or H2 has to be increased. The second thing is the equipment standards. So if you're going to check the RF performance of a system, it's going to heavily vary upon the quality equipments that you have. So we as SenRa, as network operators, we kind of tend to buy the high quality gateways that provide you receiver sensitivity level below -142 dBm for this SF12. You saw I was writing always -137 dBm for SF12, but the gateways that we purchase are going to offer you -141, -142 dBm SF12. And that comes up with a high cost, but that is something that we really want for customers. When you see an antenna, that is something that is one of the most important aspects of wireless communication system. We really take care of the antenna VSOR, return loss, and all sort of stuff. That is particularly a different discussion in the other direction. But note that equipment standard is going to make or break your RF performance. The third thing is the dense coverage. How many gateways that your end device is going to see is defining the diversity order. So if your end device is seeing just one gateway, it's a high chance that it will be seeing a packet loss when there is going to be an interference due to other end devices. So your gateway at a time should be able to see more than two gateways, and that is necessarily the function of how dense the coverage is, how your network operators have actually deployed the network in the region that you want the network in. Because higher the diversity order, higher the larger the packet success rate. So that's the key to a professional deployment. You would want to have a massive receiver height. You want to have a high quality equipment standards, and then you would want to have a really dense coverage to get a high diversity order that will give you a large PSR. Now, we understood all those things, the technical things that we have studied in section 1, 2, and 3. It's time now to talk about a case study. When I'm going to talk about case study, or you see any case study on LoRa, the first thing that you should ask the person who is claiming the range that we have gotten is these factors that we have now good understanding of. The 5 factors, that is, what was the frequency within which you were transmitting in India? The ISM band goes from 865 to 867 megahertz. So the case study that I'm going to show you, the frequency of transmission operation was from 865 to 867 megahertz, within which there are 8 channels. Out of these 8 channels, we randomly choose to transmit the mode. Then I would tell you what is the bandwidth that we started with. That was 125 kilohertz. The spreading factor that we were using during the case study that I'm going to show you was 12. The code rate was 4, and the transmission power is 14 dBm. Now, you know all these things that I've just written down. If I even have a slightly 1 or 2 digits of change in any of these, essentially changes the entire picture. If I'm not using 14 dBm, rather 20 dBm from transmission, my range is going to might get 1.5 times or 2 times. So you must ask these questions when you're seeing somebody claiming what's the range that they have gotten. So I'm just listing down the other things that matters that we have understood. Now we have a greater understanding of all these factors. The other factor within which this case study was done was the enclosure. The enclosure was a car. We were roaming around a city within it, lying inside a car on the seat, and hence the transmitter height was 0.5 meters. The receiver height, as we say, for all our network deployment is massively high. For all the gateways that you will see are actually a height of 30 meters above the ground. The environment was moderately urban, and that is something that I wanted to point out. That if you're having a rural environment, it intuitively makes sense that you might get a direct line of sight path condition and lesser multipath. But what was the environment in which we did this case study was moderately urban. I want to admit that it was not having skyscrapers as Manhattan, but that was still a moderately urban dense environment. And that's how the range that we have captured. So that is something that we really take pride in. We had a gateway and we were roaming around the city, and these are the different points where we have gotten we have captured the uplinks. So you see the color coding on the markers. The darkest blue markers are the ones that are only 2 kilometers away from the gateway, and these are the places that we have captured 2 kilometers range. The markers in the blue are within the range of 2 to 5 kilometers, and the lightest blue markers are above 5 kilometers. So that is the kind of range that we have gotten. Now let's analyze this case study better. Let's then understand the importance of a dense network. We saw this picture. We saw that the gateway was actually capturing information within the A1 region, which is within the 2 kilometers of range. So this particular region, around 2-kilometer radius, all the different sectors that you see were actually capturing the packets with a packet success rate of more than 80%. But the point to note here is that these are the positions which are ideal for the end devices to be located. So that is what we also do in a complementary fashion, that we tell our customers which are the places that your end devices would want to reside if you want to go for a POC. just give a demo. So we also tell which are the ideal locations that you would want to put your end devices for the POC, but that's a different story. The point to note here is that the A1 is the sweet spot where your end devices should reside when they are talking to the A1 gateway. But I told you that I was capturing signals on the A1 gateway in the region which was A2 and of course in region A3. So these are the regions where I was also capturing information with gateway 1, and these are like 5 kilometers, 7 kilometers, 8 kilometers above that. The question is, even though I'm receiving packets in A2 and A3 regions, is this a high class reliability solution? Do I just want to have the A1 gateway deployed in this region, expect all the end devices that are going to reside in A2 and A3 regions to communicate with this gateway? It could be a it could be a possibility that some end devices residing in A2 and A3 could not communicate with the gateway. It could or it could not. So we don't take that risk. And that's why we do a very dense network coverage. And that's what SenRa do. So you see A2, A1, and A3. This is the different regions that we saw. We understood that A1 was the sweet spot for the gateway that was residing in the center. But for the A2, even though I was receiving the packets, what we do as SenRa, we deploy another gateway at the center of A2. What that does is that it creates a sweet spot for all the devices that are going to reside inside the A2 region. Even though they are communicating with the A1 gateway, they're going to also communicate with the A2 gateway. That is going to be their sweet spot. But since all the end devices are now having a diversity order of 2, you now understand that they are more immune to interference and going to have a high PSR. Likewise, for the A3 region, even though the gateways at A1 and A2 are getting communication, we still deploy another gateway, redundant gateway on the A3 region, just so that all the end devices that are there within the A3 region are also getting a sweet spot gateway for them. What all that is trying to say to us is that we provide redundancy in the network. What redundancy does is that it densifies the network. That simply provides high quality reliability and quality of service. Even if you're not able to try to talk to one of the gateways, you have two other gateways around that you could talk to. That's the beauty of having a large, dense network coverage. Now, one thing that I was seeing the LoRaWAN 101 webinar was that what's the range that SenRa has observed when they have done some range testing in some of their projects. And that's something that I would not want to reveal. So this gateway in one of the cities in India, and we have captured a range of 14 kilometers. That is pretty huge at 14 dB in transmit power in a moderately dense environment. Note that we were actually not aiming to do a long range test. It's just that we were testing a gateway in A3 region, but it was also communicating with the gateway in A2 region. If you would have gotten a lot far, this could have changed from 14 to 25 as well. But that was not our aim, but that is what we have gotten as the longest range that we have seen so far. It actually changes every day, but that's the one that is still the largest that we have observed in this moderately dense environment at transmission power of 14 dB. The one thing that is going to be really interested for all those that have listened carefully through this webinar is this fact that all these testing that we have done was done inside a car. But then after all the testing that we have done, we are actually running a real massive water meter deployment in India, in one of the cities in India. And there are hundreds of thousands of smart water meters that are deployed, and these are the gateways that are communicating with it. Now, the enclosure, as you understand, in case of a water meter is a cement. And cement, as you now understand, that is going to offer a heavy attenuation of 35, 38, 40 dB. The transmit height is below the ground. You are not expecting the water meters to be installed on top of one floor. It's the limitation of the use case that it has to be residing 1 meter below the ground. And the use case is water meters, so the end devices are battery powered, they're not AC powered. So the maximum transmit power that they are fixed at is 14 dB. Despite all of these things, the dense coverage, high quality equipments, and massive receiver height, we are still able to capture a range of 12.41 kilometers with an 88% packet success rate from one of our end devices. And this record is actually broken every day. This is like 4 days before information. It has changed to 13 kilometers today, but that is actually changing rapidly. And that's the beauty of having really professional development. And the keys that I told you, we really take care of all those. And that actually concludes the webinar. I would now like to answer some of the questions that you would have asked in the Q&A section, and let's see if I have time for answering them. One thing I would want to talk is that if any of the case studies or the things that you have seen, if something else doesn't make sense much to you, I would recommend you to just watch the video again because it's going to be there on YouTube after this webinar, and watching it for the 2 or 3 times is going to make sense, much more sense to you. Just in case it doesn't, we are there always for you at info@senraco.com. These are the websites, these are the links that you would want to copy paste, and these are the places that you would want to go for to ask any doubts that you have, whether it's about understanding of LoRa or whether it's about the RF performance, it's about the case study that you would want to talk about, or just your different solution that you are actually having in your mind. I will now see if there are some questions and even if I have the time to answer those. Just note everyone, just in case we are not able to answer all the questions, uh, we are just going to ask you to please wait for a week or so, and we are going to be back with proper descriptive answers for you, and we could have a good discussion on that email chain. Cool. So let me see if some of the questions are there that are really easy and we could answer them right away. What's the difference between LoRa and LoRaWAN, Zoya? That is something that we discussed thoroughly in the previous webinar. Note that LoRa is a physical layer protocol. And one of the prominent features, one of the prominent beauty of the LoRa is to do the modulation that we understood today. All the things that are related to adding network related fields is part of the MAC layer, and that is actually LoRaWAN. So if you'd see the OSI model, you would see the different layer, PHY, MAC, and network transfer, and so on. So LoRa essentially lies in the bottommost layer, right? That is what is known as LoRa. LoRaWAN, however, rides on top of the PHY, that is the MAC, and that's where LoRaWAN resides in. You would want to check out the LoRaWAN 101s just so that you get a clear understanding, and that's where we actually discuss the difference in a better form. Okay. What is the bandwidth of LoRaWAN? You see, we generally are, when we are testing our devices, from 125 kilohertz, it's 250 kilohertz and 500 kilohertz. These are the different bandwidth ranges and within which you could transmit your signal. So that's the answer for that. Let me see if I could answer some more questions. Can you differentiate between chirp and chip? I knew this could have gotten, so the chirp is a RAM function that changes its frequency from lowest frequency to the highest frequency. So the chirp is comprising of different chips. So it's just like if you're having a chirp, just imagine as if it is broken down into 4 parts. Those parts are known as chip. And chip is the time, so the chip time is defined by the time for which the ramp would go from FL to FH. I would better come up with an answer with a visual for that, just in case that didn't make much sense to you. And that's what we could do for that. Why PSR? Why is PSR less at some places? Question. Okay. So the question is that why is that some places are offering a high PSR and some places are offering a low PSR? Guys, note that when your signals are getting transmitted from that same position on Earth, uh, every time you would send the packet, every time you will see a different RSSI because the path loss changes heavily. If you would see mathematically, it's just a Gaussian random variable with a mean and sigma. What that means is that if you're having a path loss of 150 dBm, then it not necessarily be going to be 150 dB for all time, but it's going to vary from minus 140 to 160. So that is a Gaussian random variable. That means that your path loss is going to change from a certain range to a certain range. So that's why it could happen that sometimes your path loss exceeds the receiver sensitivity at the receiver, and that's why the signal cannot be demodulated. But at the other times, it could just be get demodulated because it was not incurring a very high path loss. So that's why some regions, since they have path loss having a Gaussian random variable with a means 0 or mean mu and sigma, and the way that that is going to change is going to define whether or not you're going to have a packet success. So that's why the packet success rate is different. We could have a better discussion on that on an email chain. I would love to do that. Thanks for everyone who is written good things for the webinar. Okay, you're looking for a good simulator compatible with LoRaWAN protocol. You would want to just check a couple of research papers that talk about LoRa Sim. So that was made on Python using SimPy module. An advanced version of a simulator for the LoRa Sim was LoRaWAN Sim, but I don't think that if it's open source. But the one that is open source and that is very heavily used in wireless communication industry is the NS3 simulator. So some people from Italy have actually made that simulator on NS3, the network simulator 3, and we have a module for LoRaWAN there. So that's where you would want to go for, but that would have an upfront resistance of learning the NS3 because it's heavily C++ based, but that is something that you could do. It's like very sophisticated software, and you would want to learn NS3, and then you could use the module of LoRaWAN to simulate the LoRaWAN protocol. It also has ADI enabled and a lot of stuff there. Uh, So let's see if we could find another question. So you said that does any other multipath signal also have a low attenuation reaching the receiver? I'm unable to get the complete question, but what I'm trying to understand from this is that you're saying we consider that when the signals are going to transmit from one position, the receiver is going to receive simply different ensembles from different reflections or diffraction or scattering. All right. The diffraction in most of the path loss models, if you would see Lee model or if you're working on Wolfish model, you'll see that the the diffracted signal is having the least attenuation compared to all the reflected or all the reflected or the direct path. So that's why I consider that the diffracted signal is having the lowest attenuation. Of course, there are going to be different signals that are going to offer you different attenuation that is defined by the delay spread. We could have a better discussion on that. If you know what delay spread means, that there are going to be different attenuation and hence different power levels from different multipaths that you've received that are having different attenuation, of course, and delayed in time. But we are really caring about the ones that offers the least attenuation. In most of the cases, the diffracted signal. So we are taking diffracted signal as the least attenuation path. Yeah, but there are more than a diffracted signal that are there. So Vijit has asked whether mesh or star topology has been deployed in LoRaWAN while RF communication. So LoRaWAN is a star of stars topology. It doesn't support mesh. So LoRaWAN is a backlayer protocol that only supports stars of stars topology, right? So what that means is that your end devices cannot communicate within themselves. They're going to just communicate with the gateway. And then all those gateways are going to go through a common NNS, and that's how the stars of the stars works. Note that some of the researchers have also worked on LoRa Mesh, and that is also something that you would want to read about. But the LoRaWAN itself is only stars of stars topology; it doesn't support mesh. Yeah. FLoRa simulator, I remember it's on Omnet. I started using it, but it actually doesn't support the ADR. So ADR is one of the most prominent, what to say, feature of the LoRaWAN protocol that helps your end devices adapt to the data rate or transmission power that they would want to use. But Omnet FLoRa simulator, I don't know if it has been updated, but at that time it might or might not have supported ADR. More importantly, it doesn't support the spreading factor orthogonality. It says that two spreading factors colliding in time are going to be just, you know, don't interfere at each other at all. So the quasi-orthogonality of the spreading factor is not there in the FLoRa simulator maybe. ADR could have been there, but the spreading factor orthogonality is a feature that's not there. We could talk on the simulator mode, which one offers what. I would strongly suggest for the NS3, yes, because FLoRa doesn't support the quasi-orthogonality, and I don't think if it also supports the downlink communication, but I think NS3 once does that. Yeah. Let me see if I could answer two more questions because we have run out of time. Uh, any case studies for smart metering solutions? Please share. Yes, which is of course, you could just reach out to us or we'll reach out to you just in case you would want to see what are the different smart metering solutions that we have offered. There are some POCs that are projects that are going on, and we would want to deliberately discuss them one by one with you on an email chain. That's the best thing that we could do together. Yeah. On any use case on water metering, guys, we just spoke on the water metering use case. It's one of the cities in India. I cannot disclose that, but that's where a massive scale water meter deployment is going on, and that's where we are providing the network as a service. So the case study that you saw was solely for the water meters that they are there. So every day those water meters are connected to our network server, and they're analyzing those water meter readings. So you are actually having one of our use case running on water meters. Um, um, just in case some of the answers are still not being answered by me, we'll reach out to you within 2 weeks of time, and we could have a deliberated discussion on that, because it's kind of hard to just speak about something and we're not having some visuals and then explain it to someone. So we would have that discussion on an email chain. We'll just discover things good together and see what is something that you didn't understand and how we could, together figure out what that means. Thanks everyone for all the comments that you have been giving. We would close this webinar for today. I will again say these are the different links that you would want to capture, you would want to go. And we'll reach out to you for some of the questions, of course, within a week or 2 times. Thanks everyone. Thanks a lot for your time. That was a heavily technical discussion. We'll come out with more technical discussions like that and more case studies, and see you in the next webinar. Thank you all very much.